Welcome back to AI.Code.Cast, where we take these deep dives, into all sorts of cool algorithmic problems.
Yeah, the kind of stuff you might bump into out in the wild.
Exactly. So today, we're looking at something, well, it sounds kind of simple at first,
It does.
but trust me, there's some tricky bits hiding under the surface,
Oh, yeah, definitely.
ready to dig in.
Absolutely. Let's do it.
Okay, so imagine you're putting on this massive flower festival, right?
Mm-hmm.
And you've got to make, let's say, M bouquets.
Okay.
But here's the catch. Each bouquet needs like K flowers, but they got to be blooming right next to each other.
Adjacent is the fancy word.
Yeah, adjacent. So you've got this array, we'll call it bloom day. It tells you when each flower is going to bloom.
Right, like our flower schedule.
Exactly. The big question is, what's the earliest you can have all your bouquets ready to go?
It's like a floral time management puzzle.
It really is.
Gets pretty interesting, especially when you start scaling things up.
For sure. Okay, so let's say our bloom day array is 1, 10, 3, 10, 2. Simple example to start.
Mm-hmm.
We need 3 bouquets, and each one just needs 1 flower for now.
All right.
I'm picturing it, like rows of flowers.
Visualizing always helps.
Right. So on day 1, only that first flower pops open.
Yep.
Day 2, the last one joins in. But we can't actually make all 3 bouquets until day 3. Right?
I got it. That's when we have enough flowers blooming next to each other.
Okay. Makes sense when you see it laid out like that. But now let's get real.
Okay.
What if we were just regular folks, no coding superpowers? How would we even tackle this?
Well, if we want to keep it simple,
Mm-hmm.
probably just start trying stuff out, brute force it.
Brute force.
Yeah. See if we can make enough bouquets on day 1. If not, try day 2, day 3, and so on.
Okay, I can see that working,
Yeah.
but I'm already getting tired just thinking about it.
It's definitely not the most graceful approach. Gets slow when your garden's the size of a football field.
Right, like imagine 100 flowers blooming over weeks. There's got to be a smarter way.
Oh, there absolutely is. But before we jump into that, let's not overlook a crucial detail.
Oh, like what?
What if we simply don't have enough flowers to make all the bouquets we need?
Oh, good point. We could be searching forever for a solution that doesn't even exist.
Exactly. So before we even start, we got to make sure we've got at least M times K flowers total.
Makes sense. If not, it's impossible. Pack it up, go home.
Haha, pretty much. Saves a lot of wasted time.
Okay, so let's assume we do have enough flowers. We're not going to brute force it.
Nope.
What's the next step up? What's a more clever approach?
Think about looking up a word in the dictionary. You wouldn't just flip through every page from the start, right?
No way. You'd use the alphabet to zero in on the right section.
Exactly. We need a way to jump ahead in our search instead of checking every single day.
So instead of starting on day 1, maybe we could skip ahead, check a day somewhere in the middle.
You're getting the idea. That's the heart of binary search.
Binary search. I like the sound of that.
It's super powerful. Let's say our bloom days range from 1 to 100. Instead of going one by one, we check day 50 first.
Okay.
If we can make all the bouquets by day 50, then we know the earliest day's got to be somewhere between 1 and 50.
And if not, it's got to be between 51 and 100. We've cut the problem in half already.
Exactly.
Yeah.
One check, and our search space is half the size. But to do this repeatedly, we need a reliable way to say whether a given day even works for our bouquets.
Right, like a quick test to see if we can make enough bouquets on that day.
Exactly. But how do we do that efficiently?
Well, we need to know how many groups of flowers are blooming together on that day, right?
You're on the right track. If we can quickly count those consecutive blooms.
We can compare that to the number of bouquets we need.
Now you're thinking like an algorithm designer. Let's dive into that more in part 2. So we're trying to make this binary search work for our flower bouquet problem.
Right, and to do that, we need a solid way to count up those consecutive blooms.
Exactly. For any given day, we got to know how many groups of flowers are blooming next to each other.
I'm thinking we'll need to go through that bloom day array again.
We will, but we can do it cleverly.
Okay, I'm all ears.
Yeah.
How do we make this efficient?
All right, so let's say we're checking a particular day, call it mid. We'll start by setting up a couple of variables.
Okay, variables for what exactly?
One, to keep track of the bouquets, we can make, let's call it bouquet count.
Makes sense.
And another one, let's call it consecutive flower count, to keep tabs on how many flowers are blooming in a row.
So we start at 0 for both of those, right?
Yep. Then we go through each flower in our array.
And for each flower, we check if it's bloomed by that midday.
Exactly. If it has, we bump up that consecutive flower count.
Okay, so if we have 2 flowers in a row that have bloomed,
Consecutive flower count becomes 2.
got it. What if a flower hasn't bloomed yet?
Ah, that breaks the chain, right?
Right. We need those flowers next to each other.
Exactly. So in that case, we reset consecutive flower count back to 0.
Start a new chain.
Yep. Now, here's the crucial part. As we go through each flower, if consecutive flower count reaches K, that's the number of flowers we need per bouquet.
We've got ourselves a bouquet.
You got it. We increase bouquet count by 1 and reset consecutive flower count back to 0.
Ready to start counting the next bouquet.
Precisely. So by the end of our loop...
You know exactly how many bouquets we can make on that midday.
Exactly. And then it's decision time for our binary search.
Okay, let's walk through that. So if our bouquet count is equal to or more than M,
The number of bouquets we need.
right, then we know that midday, or maybe even an earlier day, could work.
Exactly. So we narrow our search, focus on the days before mid.
And if we don't have enough bouquets yet,
Then we got to look at later days, the ones after mid. Again, cutting our search in half.
we're zeroing in on that perfect day. It's like Goldilocks and the 3 bears, but with bouquets.
Haha, I like that analogy. Now you might be thinking, isn't it more efficient to combine all this into a single process instead of having a separate helper function?
Yeah, actually, that was on my mind. It seems cleaner, less code, but does that really make it faster?
Good question. It might feel more streamlined, but when we look at the big picture, the time complexity, the overall efficiency stays the same. It's still O(n) log D, where n is how many flowers we have, and D is the range of bloom days.
So even though the code looks tidier, the underlying performance is the same.
That's right. Sometimes different approaches lead to the same level of efficiency.
Huh, interesting. There are multiple routes to the same destination.
Exactly. And speaking of different routes, remember that union find approach we mentioned earlier?
The one of those little flower communities.
What's the one? Even though it's not the most efficient solution for this specific problem,
Yeah.
it offers a really interesting perspective on the problem.
I'm all for broadening our horizons.
Perfect. We'll explore that in our next segment.
All right, back for the final round of our AI.Code.Cast deep dive. We've seen how binary search can really speed things up when figuring out the earliest day to make our flower bouquets.
It's a powerful technique, that's for sure.
But now we're going to shift gears a bit.
Time for something different.
Exactly. We're going to check out this thing called union find.
Yes, union find. Always a fun one.
I gotta admit, it sounds a bit mysterious.
It's a cool concept, though. Gives you a whole new way to think about the problem.
And that's what I'm all about, right?
Yeah,
Seeing things from different angles.
absolutely. Sometimes the less obvious path can teach you the most.
So remind me, how does this union find thing actually work? I remember the flower community analogy.
Right, right. So imagine each of our blooming flowers is like a node in a network.
Okay,
If 2 flowers are blooming right next to each other, they're connected.
like little buddies.
Exactly. They form a little flower community. And Union Find, it helps us keep track of these communities as we go through the different blooming days.
Okay, I'm picturing these little connected groups of flowers. But how does that help us figure out the minimum number of days to make all the bouquets?
Good question. So for any given day, we can use Union Find to group all the adjacent blooming flowers into these communities. And each community, that basically represents a potential bouquet.
Ah, I see. So the goal is to find the earliest day where we have at least M of these distinct flower communities.
You got it. That means we've got enough groups of adjacent blooms to make all our bouquets.
Makes sense. Now, Union Find has these 2 main operations, right?
Yep. Union and Find.
Right. Union is like merging 2 flower communities together if they're next to each other.
Exactly.
And Find helps us figure out which community a particular flower belongs to.
Exactly. So as we go through each day, we look at every flower. If a flower has bloomed, we check out its neighbor. If the neighbor's blooming too, we use Union to merge them into the same flower community.
It's like we're playing matchmaker for the flowers.
Haha, kind of. And we do this for all the flowers that have bloomed on that day. Then...
We count up how many separate flower communities we have.
Exactly. And if that count is greater than or equal to M, the number of bouquets we need.
We know that day works. We can make all our bouquets.
Right. But we don't just stop there, do we?
Nope. We want the earliest day possible.
Exactly. So we keep looking at earlier days until we can't make all the bouquets anymore.
We're finding that sweet spot, the minimum day.
Precisely. Now you might be thinking, if Union Find can solve this problem,
Yeah.
why isn't it always the best way to go?
Great question. It seems pretty clever.
It is, but it has its downsides. All those union and fine operations we're doing,
Hmm.
they can actually take a bit of time, especially when you have tons of flowers.
So it's not as efficient as binary search.
Not usually, no. Binary search, with its logarithmic time complexity, it tends to be much faster, especially when dealing with lots of flowers and a big range of bloom days.
So even though Union Find gives us this neat way of picturing the problem with these flower communities, it might not be the speediest option.
That's right. But remember, sometimes there are trade-offs. Code readability, the elegance of an approach, those can be valuable too.
Absolutely. The best tool for the job isn't always the fastest one.
Exactly. And sometimes understanding different approaches, even the less efficient ones,
Mm-hmm.
it can really deepen your understanding of a problem.
Totally agree. It's like having more tools in your coding toolbox.
Couldn't have said it better myself. Well, that brings us to the end of our AI.Code.Cast deep dive.
We explored binary search, we saw how to count those consecutive blooms, and we even took a detour into the world of Union Find,
And along the way, we learned some key things about algorithm design.
like how to break down a problem, how to think about efficiency, and how to consider different approaches, even if they're not the most obvious.
It's all about finding the right balance for the specific challenge you're facing.
Well said. A huge thanks to everyone for joining us on AI.Code.Cast.
Until next time.
Keep coding, keep exploring, and we'll catch you on our next deep dive.